Okay, so in this session we're going to continue to expand the different types of special functions that we were able to differentiate. So in previous work we looked at how to differentiate the exponential function. We also looked at how to differentiate the natural log function. And when we combine those with the quotient rule, product rule, chain rule, it means that we are now able to differentiate some quite complex mathematical functions. There's still more to do though, and in this section today we're going to be looking at how to differentiate trig functions, sine, cos, tan, and the other ones that you've learnt recently in pure. Excuse me. When we looked at differentiating the exponential function, I talked about power series and how e to the x could be written as a series of increasing powers of x, an infinite series of increasing powers of x. Such series also exist for sine and cos, and those are shared here. And this is a really nice way of demonstrating the derivative of sine and cos. So if, as you see here, we have got that sine is an increasing series of x, where you've got x minus x cubed over 3 factorial plus x to the 5 over 5, so you can see it's an increasing sequence where x is being raised to an odd power. If we want to differentiate that, so if we want to differentiate sine of x with respect to x, so that's our function. So the first term is x, so when I differentiate that, I get 1. When I differentiate this, I'm going to get minus 3 x squared over 3 factorial, where 3 factorial is 3 times 2 times 1, which is 3 times 2 factorial. Then I've got the x to the 5 function, which will be 5x to the 4 over 5 factorial, which is 5 times 4 times 3 times 2 times 1, or 5 times 4 factorial. X to the 7 will be minus 7x to the 6 over 7 times 6 factorial, and so on to infinity. So if I tidy that up now, you see that 3 will cancel there, giving me 1 minus x squared over 2 factorial. 5 cancels here, giving me plus x to the 4 over 4 factorial, minus x to the 6 over 6 factorial, and so on. And if you look at the power series for cos, you can see that what we've got by differentiating sine is the power series for cos. So therefore, when we differentiate sine of x, what we get is cos of x. Let's see what happens when we differentiate cos. So when we differentiate 1, we get 0. When we differentiate x squared, we get 2x over 2 times 1. When we differentiate 4x squared, when we differentiate x to the 4, we get 4x cubed over 4 factorial, which I'm going to write as 4 times 3 factorial. You can see why, because it allows us to cancel. minus 6x to the 5 over 6 times 5 factorial, and so on to infinity. So these will cancel, and what I end up with is minus x plus x cubed over 3 factorial minus x to the 5 over 5 factorial, and so on. So if we look at the power series, we can see that, well, we've got the right powers to match with sine, but the signs are the wrong way around. So if we were to take the minus sign out, then that would change the signs that we have in there. So now I've got minus x cubed plus x to the 5. So that's equal to minus sine of x. So when we differentiate cos, we get minus sine. So therefore d dx of cos x is minus sine of x. So when you differentiate sine, you get cos. When you differentiate cos, you get minus sine. We do need to show how to differentiate sine and cos from first principles, but we'll do that in a separate session, because it's just something that you're going to have to learn, whereas what we want to focus on now is actually using these two relationships to enable us to differentiate ever increasingly complicated functions.